Hello everyone. In our fourth video on signal processing, we are going to look at signal characteristics and metrics. So one of the first thing we have about the signal is its energy. So if the signal is continuous, and I mentioned it in one of my previous videos, if you square the signal and integrate it over all time, that is going to be the energy of the signal. And using Parseval theorem, you can also integrate it over all frequencies. So if you get the x of f and square it, so there is no negative part to cancel positive parts, and square it over all range of frequencies, that will also give you the energy of the signal. Now, if the signal is discrete, so you only have signal over specific n values, and n here is the sample, the number of the sample, right? So sample number 1, sample 2, 3, and so on and so forth. Then this integral becomes a sigma. Sigma goes from negative infinity to positive infinity. Still, the signal value needs to be squared to avoid adding positives and negatives. And of course, it represents the total energy of the signal over all time. If you want only an energy of a signal over a specific period of time, then you have to basically only do it from so much time to so much time, okay? Now, for instance, if your function is an exponential function and this is the step function, the energy of it is going to be 1/2. Well, how come? We can easily go ahead and perform the integration. So this is going to be the integral from negative infinity to positive infinity of now, since this is step time and step function is only defined over positive numbers, so this we have to change it now to 0 to infinity. So the magnitude of it becomes 1, and when you square that, this is going to be e to the negative 2t, right? Because it's e to the negative t to the power 2, and then dt. And you know the integral of this is e to the negative 2t over negative 2, and calculated at infinity and 0. At infinity it's 0, at 0 it's 1, but there is a negative 1 which cancels with this negative, and you're going to get 1/2. So the energy of a decaying exponential with a power 1 or an exponent 1 is 1/2. There we go, right? So this is the energy of the signal. The next thing we have is the power of the signal power, which is the average of this is the energy per time, basically. So an average power for a continuous signal is defined as the energy of the signal over one full period divided by the period. So if the signal is periodic between negative t to t, and you integrate it and divide it by that whole time and let this t goes to infinity, so it involves the entire basically range of signal, that is basically called the average power of a continuous signal. Now, if it's discrete, of course, you have to basically square the signal, sum it up instead of integrate from negative n to n, and divide it by the whole range. And going from n of negative n to n of positive n, the total number of n's that you have is 2n plus 1, because there is n of 0 in the middle. And then once you divide it, you let n go to infinity. So this is the power for what? For a discrete signal, okay? And of course, it represents the average signal intensity. For instance, if you have a harmonic function, a cosine omega t, the power, you can show that it's a squared over 2. So let's do that here. You know that if I want to do it, it is going to be the limit of 1 over 2t. The integral goes from negative t to t of, this is going to be a squared and cosine squared of omega t dt. And omega and t are related to each other, right? Because omega is 2 pi over t, as you know. Okay? So I need to take this limit, and in this limit, let t go to what? To infinity. So first thing is, I need to calculate this a squared cosine omega squared. A is a constant. I can get it out of the integral. So this is going to be the limit of a squared over 2t as t goes to infinity of. So it is going to be basically the integral of 1/2 is going to be 1/2 t, so it's going to be t over 2. And that one is going to be 1/4 sine of 2x. So it is going to be sine of 2. And in this case, your x is omega t. So it's going to be like that. And then divided by 4. And this thing is evaluated at t and negative t. Now, when you plug in t here, this is going to be omega t capital and negative omega t capital. And if you look here, omega times t is 2 pi. And sine of 2 pi and negative 2 pi are both 0. So this term is going to go all to 0. This term is going to be t minus minus t. So that's 2t. With that, you're just going to get a t. And finally, these 2 t's would cancel, and you're going to get a squared over 2. Okay, so this is the signal power for a cosine. It's going to be the amplitude squared over 2. The next notion that we have, we call it the DC, direct current or average value of a signal, which represent its non-varying or constant component. So for a signal, we integrate it over a range, a period, divided by the period, and let this t go to infinity. So this is clearly the definition of average. But we allow t to go to infinity to be the average over the entire span of the signal. And if it's discrete, very similar. We add all of these x's. Instead of integrating them, we divide it by all of the indices, and we let the number of indices go to infinity. That's the same thing. And you can show that if your signal is a harmonic plus some constant value, which we might call it bias, actually that bias is your DC component. Because if it's just a harmonic, then your signal will oscillate like b sine omega t. It is going to be like this. So this is b and this is negative b. So the average value of the signal is 0. But if you shift it up by a value of a, now you're looking at something like this. So this number here is a plus b, and this number here is a minus b. And the average of the signal is here, which is exactly a. So, and it's very easy to show that. So I'm not going to do this. I know you can all do it yourself. So the average for a harmonic is the value of the bias. Okay. This is called the DC value. Now we have another value that is related to the power. This is called root mean square or RMS value. Okay. So let me just add it here. So this is called root mean square or RMS value. So this root mean square basically shows the constant value that if the signal was a constant signal, if the signal was equal to x RMS and it was a fixed number, if the signal was a constant number, the power of this signal that is equal to x RMS is equal to the power of the actual signal, which is basically this guy. So if, again, we make the signal a constant, the power we get from this formula should be what? Should be the same as if we had it constant at this value. And if you look at this, if you just look at this, this is the exact same thing that you have in that power formula. Look at that. That's the same thing, except for integrating it from negative t to t and dividing by 2t, or integrating it from 0 to t and dividing by t. That's the same thing. So this guy here is exactly what you see under that square root, right? And you know that if your signal is just a constant x RMS, the power of that signal, or the energy of the signal for that matter, the energy of the signal is going to be the value squared. So the energy of fixed x RMS is simply going to be x RMS squared, because you only have a single value, and That is, of course, you have to integrate this over all time, but if you integrate it from 0 to t and divide it by t, because this one comes out, you get x RMS times t divided by t, so your power, which is energy divided by time, your power of the signal will simply be what? The x RMS squared, right? For that reason, if I take the square root of this power, this is the power of the signal, that is going to be what? That is going to be the definition of x RMS. So x RMS is the square root of power. Now, if it's a discrete signal, of course, again, we square the signal and we go from n of 0 to n minus 1 divided by n and take the square root. Again, that's the exact same definition as this one, except that instead of going from negative n to n, we are just going from 0 to n, or n minus 1 in this case. So we go from 0 to n minus 1 and we divide by n, but that's the exact same definition. Okay, so it's an equivalent DC level. Equivalent in what? In power. So it's not the DC value, it's an equivalent DC value such that the x RMS signal has the same power as the original one. Now, of course, if it's a cosine omega t, the x RMS is going to be the it's going to be the amplitude divided by square root 2. Where does that come from? Well, it comes from here. Remember, the power is a squared over 2, so just take a square root of that. This is basically what? The square root of the power, which is a squared over 2. So it's going to be magnitude or amplitude of a over square root 2, or 0.707a. 71% of a, that is going to be the RMS value of a harmonic function. Okay? Let's move on. The next two notions that I want to introduce to you are time-limited and band-limited signals. A time-limited signal is a signal that is only defined for a finite duration. What duration? I mean in time. So if you plot the signal versus time, the signal is only non-zero for so much of time. After that, outside that range, is all zero, like this rectangular function. Okay? So a rectangular function is clearly what? A time-limited signal. On the other hand, band-limited means the frequency content of that is limited. So if you plot the Fourier transform of that, magnitude of it versus f, clearly, again, in some range, it is non-zero. Outside that range, there is no frequency in the signal. So this is band-limited. This guy is what? Time limited. Now, there are two other things we want to discuss. First, I wanted to talk about this one, but I decided to change. So first, let's look at one example. Is the rectangular pulse in the time domain, this guy, is it both time and band limited? The answer is no. This is clearly time limited, but if you remember from my previous lecture when I performed the Fourier transform on this rectangle, you got the sinc function, right? Let me show you that. So this was the time, the rectangular time, which is time limited. But if you remember this frequency content of it, this guy keeps going forever. Although it gets smaller and smaller, but it becomes zero only when omega or f goes to infinity. So in the frequency domain, this signal is not limited, only in the time is limited. And the other way around, if you look at the rectangular function in the frequency domain, which is band limited, in the time domain, it's a sinc function, which is not time limited. So the important thing, which we call the uncertainty principle, says no signal can be perfectly time limited and band limited. Okay, there is no signal that is perfectly both of them. And there is even a formula for that, which says if the duration of the signal in the time domain is delta t and the frequency band of it in the f domain is delta f, the product of them is always bigger than or equal 1 over 4 pi. Now, of course, when you are not one of them, one of these two will be infinite. So, of course, infinity is bigger than 1 over 4 times pi. But clearly you see that there is always a lower bound, and in matter of fact, this guy is always one of these two will be infinite. Okay, and you might say, well, is there any case that this could be perfectly equal to 4 pi? Well, because there is an equality, if your function is a Gaussian function in the time domain, in the frequency domain, it's also a Gaussian. And although practically both of them are infinite, but if you consider a range that after which they are perfectly close to zero, right, like 3 sigma plus and minus on each side, still you're looking at a minimum of 1 over 4 pi. Okay, so no signal can be both of them at the same time. Next topic, signal to noise ratio, very important topic. Definition is the power of the actual signal divided by the power of the noise that is in the signal. If you want to convert it to decibel, because most of the time this SNR is described in decibel, then you take a log 10 of this ratio and multiply it by 10. Okay, then you have it in decibel. What does it indicate? The bigger it is, it indicates that your signal is bigger compared to noise. Basically means your signal has a better quality and low amount of noise in it. So bigger SNR is always desirable. Low SNR means your signal is very noisy. For instance, if the power of your signal is 10 milliwatts and the power of noise in your signal is 1 milliwatt, then if you plug 10 and 1 here, right, that is 10, like 10 of that is 1 times 10, you're going to get 10 decibel. So a 10 decibel is what you can get for whatever the signal is. Now you might say, is 10 decibel a good number or is not a good number? Well, that very much depends on the application, but let's look at a general interpretation of SNR. So if it's a number less than 0, what does it mean? When it's less than 0 means this logarithm is negative, and this logarithm is negative only if this numerator is less than the denominator, means the power of the signal is less than the noise. Okay, and when would you have signal less than the noise? When basically what you get is mostly noise. Okay, not much of a signal in it, is a lot of noise in it. That means your signal is extremely poor and you cannot really use such a signal. If it's between 0 to 10, what does it mean? Means that if we go back to this ratio, this time the noise is, signal is bigger than noise because this number is positive, but it's not more than 10 times bigger. It's only between 1 to 10 times bigger. For instance, it could be 4 times bigger, 5 times bigger, and logarithm of that is a number between 0 to 1. When you multiply it by 10, you get between 0 to 10. So you see that when this ratio is 10, you get 10 decibel. So below 10 decibel means the ratio is less than 10. Like for instance, what? Your signal is 4 times, 5 times, 8 times stronger than the noise. Still, this means your signal is quite a bit poor, and it's not really easy to see that. Now, once you pass 10, now your signal is at least 10 times stronger. 20 means 100 times stronger than the noise, and that is when you go toward 20, now you get a relatively fair signal. So if you have low fidelity communication or detection or something, this could be good enough. Once you go to 30, which means 1,000 times stronger, now you have a good signal, which is clear. There is a little bit noise in it. If you go to 40 decibel, now you are looking at 10,000 times stronger. Now you're looking at a high quality signal with bare minimum noise, and anything above 4 decibel, that basically means it's almost noise free. So if you're looking for an answer, what is a very perfect clean signal? Something around 4D, a little bit over or close to 4D, that is like perfect. Which signal is relatively acceptable? At least 20 and above. this is the range. This range here is not really good. The range below it is good. And once you pass 30 decibel is great. After 40 is perfect. Okay. Again, which one of them is the one that you need? It does depend on the application. For instance, if you're looking at an audio system, in an audio system, you can see that, for instance, in a telephone, when you hear to the voice on a telephone, the SNR for it is about 30 decibel, which is, based on this definition, it is what? It is a good signal, which means the signal is understandable, but typically it's not the best. If you look at FM radio, now you're looking to 50 to 70 decibel, which means really good quality. CD quality audio about 90 decibel. It's amazing quality. And if you have a professional digital recording device, you can get plus 100 decibels, which means basically there is no noise and the noise has been completely filtered out. Okay, so you can see some ranges in an audio system. If you're looking into communication systems, for AM radio, you're looking at 20 to 30, FM radio 40 to 60, analog TV video 40, digital modulation devices 10 to 25, which is not really good. And if you have optical fiber links, now you're also looking at 20 to 40. And finally, if you're looking at sensors and data acquisition and so on, if it's a cheap sensor, you might get 30 to 40. So even cheap sensors are really good. If you're looking at an industrial sensor, you might get 50 to 60. And if you're looking into a scientific one, now you can get 80 to what? 100 decibel, okay, of SNR. So now you get a better idea of what is good, what is not. Okay, the final thing we're going to look at in this video is called energy spectral density and power spectral density, ESD and PSD. Now, I have seen some places they call it a spectral power density, so they swap these two words. Okay, so they call it SPD, but really it's really power spectral. It's a spectral density, whether it's for energy or power. And what is it? So remember that in the time domain, you square the signals to show the energy. The same thing in the frequency domain, if you square the amplitudes, you're looking at the energy for that specific frequency, right? And if you basically square the energy over a range and divide it by that range of time and take the limit, that is called what? That is called the power spectral density, which shows how much power is distributed per frequency. For instance, if you look at this image, which is taken from the Wikipedia, this is the power spectral density of a fluorescent light. Okay, so this is a fluorescent light. And if you look at it, you see that the maximum power is in these two frequencies, whatever they are, right? Seems like one of them is about 600, 1020, and the other one is about 550, 60. So these are the frequencies that have the maximum energy of the fluorescent light in them, okay? Right? So this is the PSD plot for basically a PSD that's acquired for a fluorescent light. Now let's look at one example together, which is also carrying a very important formula in it. So one thing I want to show you and talk about it is called white noise. What is white noise? White noise is a signal that if you look at the power spectral density of it, it is constant. It's not like this, that is mostly concentrated around a specific frequency and the rest of it is small. It's constant power over all frequencies. In other words, from each frequency, you can imagine there is an equal amount of power in this signal. That's why this signal is called white noise, because similar to white light that has all frequencies or colors in it, This noise also has all frequencies in it, so we call it white noise. Now, one thing is, would you see the white noise with the way we define it, perfect constant PSD? Would you see such a signal in real life? The answer is no. There is no such a signal in real life. It is a signal with infinite energy, and you basically don't see such a thing. But there are some processes that the signal that they can make could be very close to a white noise. So this is a theoretical thing, but many things in reality could be close to it. Like what? One of the examples that you have is the thermal noise in resistors, which is the random motion of electrons in a resistor. Okay, the effect of that can generate on the voltage or the current passing through it could show itself like a relatively close to a white noise signal. And you might say, what is this constant and not if it's thermal noise in a resistor? This is equal to 4 times K times T, where this T is the absolute temperature of the resistor in kelvins, okay? And this K here is what we call the Boltzmann constant. Okay, which is like 1.38 times 10 to the negative 23 joules per Kelvin. Okay, so this is one example in real life that you get something close to a white noise. Another thing I have to just briefly mention is many times you hear this word AWGN. What is this? This W is white and this N is noise, but there are two extra things added to it. One of them is A, which means additive. One of them is G, means Gaussian. Okay, so this is what? This is additive white Gaussian noise. Why is it called additive? Because your actual signal, if it's whatever you want to call it, for instance, S of t, has the underlying actual signal, you might call it P of t, plus what? Plus this noise of t, okay? So this noise is added to your signal, and this is how it's modeled. That's the real signal is the underlying one time plus the noise. And this noise is a white noise. Now, why is it called Gaussian? Because the amplitude distribution in this N, if you look at this white noise in the time domain, the amplitudes that you see could either be like, in this case, like a regular random white noise. They could be arbitrary distribution for the amplitude in N. But if it's Gaussian noise, the amplitude distribution in N will follow what? Will follow a normal distribution with average of 0 and with the standard deviation of sigma squared. Okay, so the amplitude distribution will be what? Will be Gaussian. Now, if you're wondering how does a white noise or white Gaussian noise look like in the time domain, let me show you that. So it looks just like that, okay? You see that the signal is all over the place. You don't see really any pattern. The average of the signal is 0, but these amplitudes that you see, they could or could not follow a normal distribution or arbitrary one. If it is a normal distribution, then we call it AWGN. And in MATLAB, you have a white noise block. It's called band limited white noise block that you can do in MATLAB, in Simulink, okay? And there is a command for it in command window in MATLAB as well, if you want to generate it. Okay, now that we know a little bit about this white noise, let's go back and explain the example. So the example says this: you have a system, and the system is linear time invariant LTI system. Okay, if you don't know what an LTI system is, please watch the video that I have on my channel under playlist controls, and you know all about it. But basically, linear means the governing differential equation of the system between input and output is linear, and time invariant means that the parameters in that differential equation do not depend on time. So you have a physical system, the input comes in, this input is called W of t, and an output goes out, this is called Y of t. This system is linear, and the transfer function of that in the time domain, which we call it the impulse response of the system, is called H of t. So the Laplace of this H is H of S, which is Y of S over W of S, okay? And for this system, the impulse response is a decaying exponential. Good. Now, if I know that this input is a white noise and the power spectral density of that is n over 2, I want to know what is the power spectral density for the output of the system. So if SW is constant n over 2, what is S of Y? Well, here you see this very important formula that if the system is LTI, the power spectral of input and output are related by what? Are related by the magnitude of the Fourier transform of the impulse response squared. So if you apply a Fourier on this impulse response and square it, that relates the input PSD and the output PSD of the system. And this formula is extremely important. So for a decaying exponential, as you know from my previous video, the Fourier transform is this guy here, 1 over a plus j 2 pi f. And if we get the magnitude of it and square it, this is going to be the magnitude squared, 1 over a squared plus 2 pi f, the whole thing squared. And now I multiplied by n over 2, and so this is what this is going to be the power spectral density of the output. Now, what does that mean? Well, although the input has equal power over all frequencies, but if you plot the output, so this is Sy of f, and this should be W of f. In this case, you see that as frequency getting bigger, the whole ratio will drop. At f of 0, it's n over 2a squared, and when f gets bigger, like a hyperbolic function, it drops. So if you want to plot it, this is going to be the plot. It is going to go like that, and it is going to go like this, and this value here is n naught over 2a squared. And they are both converging on both sides to 0. Okay, so this is going to be the PSD of the output as opposed to this one, which shows that you have a lot more energy in the constant value, and as your frequency is getting bigger and bigger, the energy in that frequency drops in this system. Okay, so now that you have seen so many important topics and characteristics and metrics of signals, we are going to stop this video, and in the next video we are going to talk about convolution. Thank you, and I'll see you in the next video.